Hi there, everyone. My name is Nathan Crum, and I work for the Florida Fish and Wildlife Research Institute. And I'll be presenting on estimating right whale reproductive dynamics while accounting for uncertainty in female reproductive states. But before I start, I'd like to acknowledge my co-authors, Tim Gowan, Rob Schick, Roz Rowland, Heather Pettis, and Philip Hamilton for their help in making this work possible. So I'll be using the term recruitment frequently, and by recruitment, I just mean the process of right whale calves becoming part of the right whale population. And recruitment is one factor that limits the recovery of the North Atlantic right whale species, which that alone makes understanding recruitment important, but specifically understanding recruitment gives us an idea about how the population can change over time, which can provide context to set reasonable population recovery goals. But estimating recruitment is not straightforward because we don't always know what reproductive state females are in, and calves aren't photographically identifiable early in life. For instance, what do we know about a female that was seen without a calf during a given year? She probably didn't have a calf that year and may not have been pregnant the previous year, but it's possible that she was pregnant the previous year and miscarried. Maybe she even gave birth to a calf that died before we were able to see it, or maybe she had a calf and we just didn't see the calf when we sighted the female. But if we assume that her sightings reflect her reproductive state, that is, we assume that she was not pregnant the previous year and did not have a calf, we will underestimate pregnancy and birth rates. Also, if we try to understand recruitment with photo ID and genetic records of calves, there's uncertainty around whether there were any calves that died before we had the opportunity to identify them, and if so, how many died. But we can always assume that the survival rate of calves identified through photo ID and genetics is representative of the survival rate of all calves, but this likely overestimates survival because it doesn't account for any calves that died before being identified. To account for these uncertainties without making these assumptions, we can use a hidden Markov model. And this type of model works by connecting sightings events to an individual state. And the probability of different types of sightings events can vary across states. So, for instance, the probability that a nursing female is sighted with a calf might be high, whereas the probability that a pregnant female is sighted with a calf is probably 0. And analyzing female sightings histories within the structure of a hidden Markov model can allow us to estimate the probability of females transitioning between different reproductive states and estimate the probability of different sighting events for females in different reproductive states. So to estimate right whale recruitment, we used sightings data of all adult and juvenile females from 1994 to 2017. We categorize sightings into different events based on whether a female was seen with a calf or not, and whether a female was sighted alive or dead. We also supplemented these sightings data with reproductive hormone data. So we included additional sightings events for when females' reproductive hormones were sampled and indicated that she was pregnant or not pregnant. We aggregated these sightings event data over 2-week periods and started our model year on November 24th to coincide roughly with the start of the calving season. And so now I'll get into the reproductive states that these sightings are connected to. So we considered the reproductive state model shown here, where each state is represented by a blue oval and the arrows represent transitions between reproductive states, where gray arrows represent transitions that occur between model years, that is from November 23rd to November 24th, and red arrows represent transitions that occur between any of the 2-week periods over which we aggregated the sightings data. You can see here that we have 2 pregnant states, and that's just for modeling convenience, where the pregnant before birth year state includes females that are pregnant before November 24th that may or may not successfully calf in the next model year. Whereas the pregnant during birth year state includes females that are pregnant after November 24th in the model year that they're going to give birth in. Now this table shows just how sightings are connected to those reproductive states, where each column is a sighting event and the reproductive states in red are the reproductive states a female could be in when that sighting event occurred. So if we saw a female with a calf, the first column here, then she was in the nursing state, whereas if she was seen without a calf, the second column, she could have been in any reproductive state, and the only thing we could be sure of is that she was not dead. Now, when we put a female's entire sightings event history in the context of this reproductive state model, we can start to narrow down the possibilities of her reproductive state history. So for instance, if she was seen nursing a calf during 1 year, then in the previous year, she must have been pregnant. However, in some cases, the model can't completely narrow down her reproductive state history. For instance, if she was seen without her calf at the end of the year she had been nursing, the model doesn't assume that she was still nursing, and it doesn't assume that she had lost the calf. Instead, the model estimates the probabilities that she was either still nursing or had lost her calf. So hopefully this overview of the model has given you an idea of how it works, and now I'll present some preliminary results from one model that we have run so far. So first up, I'll go over the first pregnancy rate, where a juvenile becomes pregnant for the first time, and we modeled this transition as a linear function of a female's age. So this figure shows the estimated probability that a juvenile female has become pregnant for the first time as a function of age, where the black line represents the mean estimate and the gray band represents the 95% credible interval. And this model estimated that roughly half of females experience their first pregnancy by age 8 and 75% experience their first pregnancy by age 11. So now on to the transition from pregnant to nursing, or in other words, when are females giving birth? We modeled this transition as a linear function of the time of year. And this figure shows the probability that a pregnant female has given birth as a function of the time of year. And this model estimated that on average, half of pregnant females gave birth before December 23rd. Around 80% of pregnant females gave birth before January 20th, and around 95% gave birth before February 17th. Now in this particular model, we modeled pregnancy rates as constant across time and included group effects to model separate pregnancy rates for juveniles, resting females, and females who had lost their calf. And we also modeled the pregnancy rate for females that had miscarried as the same as that of resting females. And also, we modeled the fetal survival rate, or 1 minus the miscarriage rate, as varying from year to year. So really, this model reflects the hypothesis that annual variation in calving rates is due to variation in fetal survival rates and not due to variation in pregnancy rates. So here in the top figure, the points show the estimated pregnancy given a female had lost a calf in the previous year, was a juvenile at age 9, and was resting or had miscarried in the previous year. And so the bars represent the 95% credible intervals for each estimate. And about half of females who had lost their calf in the previous year were estimated to have become pregnant, while just over 80% of females who were resting or who had miscarried in the previous year were estimated to then become pregnant. Now the bottom figure shows the estimated fetal survival rate for each year. So for instance, the estimate for 1994 represents the fetal survival rate estimate for females who were pregnant in 1994 and were due to give birth in late 1994 or early 1995. And the pattern of these fetal survival rates over time is similar to the pattern in the number of individual calves observed each year. So we also estimated calf mortality. In this model, we modeled calf mortality as constant across time. But first, I want to mention that we accounted for the possibility that a calf was alive even if it was not seen with its mother. So this figure shows the probability of sighting a calf with its mother at least once over a 2-week period, given that the mother was sighted and that the calf was still alive. And so we modeled this probability as a linear function of the time of year. And as you can see, the probability of sighting a calf with its mother is above 95% during the calving season, but drops below 90% by midsummer and below 80% in the fall as the calf ages. Now this figure shows the estimates of average calf survival from its time of birth through the end of the model year, which is through November 23rd. And as you can see, this model estimates that about 75% of calves survive their first year of life. And this model also estimates female survival rates. And we modeled female survival rates as constant across time and constant across reproductive states. And the model estimated an annual survival rate of about 95% for females, which is pretty consistent with other published estimates of female survival. So the right whale research community has collected a lot of valuable data from individual whales over the years, and this hidden Markov modeling approach allows us to integrate that data and model it in a biologically realistic way where we can reduce the assumptions we're making about these whales' reproductive states. And ultimately, results from this model and future versions of it can provide critical information for population viability analyses and setting recovery goals. And the results can also inform us on how effective monitoring is. For instance, we can calculate the estimated probability that we miss ever sighting a calf, whether that be due to the calf dying before being sighted or surviving its first year and still not being sighted. And moving forward with this project, we're working on including visual health assessment data and latent health states in the model to evaluate how reproductive transitions are associated with females' health. And also we can use these estimates from these models to reconstruct females' reproductive state histories, which could be valuable for case studies in the future. With that, I'd like to thank my funding sources, NOAA Fisheries and the Save the Manatee Trust Fund. And thank you all for your time, and I look forward to any questions you might have for me during the meeting.